the link. So for those of you who are joining in from home, everyone in the audience has a hard copy of the course evaluation form. So please fill that out if you're in the audience. But also, Marty, Dr. Ravenhorse is going to drop in a link for the form into the Zoom chat. So please be sure to fill that out at the end of the seminar. Thanks. I think I'll let Bob go ahead and introduce Matt first off.
Okay. Good afternoon. I'm Bob Hill. I'm the soil physicist here at the University of Maryland. It's my pleasure to introduce the PhD student that Dr. Kachepsky and I co-advise, Matt Stocker. Matt got his BS degree here at the University of Maryland in the spring of 2012, and then he discovered soils. And so we actually got a job working as a hydrological research technician at USDA. He found that he loved doing research. That's what he wanted to do with his life. So he came back. Yeah, no, too bad. he came back and got a master's degree and finished that in the spring of 2017. He started his PhD in the fall of 2018. He should finish it by the end of this year, although he won't get his thesis in time to graduate this fall, probably next spring. The work on his MS degree was to look at E. coli and Pseudomonas transport in runoff and leaching and the survivability of those bacteria. For his PhD, he's looked at the spatial and temporal distribution of E. coli in irrigation ponds. In doing so, he's probably generated the largest database in existence for the spatial and temporal distribution of E. coli in farm ponds. And the practical purpose of that is two practical questions: is federal rules now require irrigation ponds to be sampled every 3 to 4 months. I don't remember, 3 or 4. And so the question is, where should you sample? Get a representative sample, and then where should the intake of the irrigation system be placed? And so those are the practical questions. So far in his PhD study, he's published 3 papers on his PhD work so far. He has another manuscript in the field of hydrology, and he's just been invited to do a submission to the Journal of Artificial Intelligence. And so he's done very well for himself. So I give you Matthew Stocker.
Thank you very much, Dr. Hill.
So my name is Matthew Stocker, and the title of my talk is Monitoring and Predicting Microbial Quality in Irrigation Ponds. As you know, my committee was chaired by Dr. Hill, as well as Dr. Kachepsky at the USDA. Dr. Davis in Civil Engineering is on the committee, as well as Dr. Jarwood and Sherman in ENST. So, okay. To start today, just going over the presentation outline. And basically everything in green is something that I'm going to cover today, and everything in orange is something that I wanted to, but there's just not enough time to delve into it. And in that sense, I recommend, if it's of interest to you, to read the dissertation document. So I'll start with background and objectives, and then we'll move through some of the items marked in green. So foodborne outbreaks in the United States and abroad are responsible for a large economic and health burden. In the world, roughly 1 in 10 people will contract foodborne illness annually. In the United States, this is roughly 1 in 6. And a 2015 study found that the median healthcare cost associated with foodborne illnesses in the United States was about $15 billion. There's also negative economic impacts, including product recalls, wasted food, buyer hesitancy. And in 2013, this was estimated to be about $7 billion annually. Now, irrigation waters as a source of contamination. A 2013 study found that 46% of foodborne illnesses were a result of eating contaminated raw or minimally processed produce, such as lettuce, other greens, tomatoes, onions. And contamination can occur in a wide variety of ways, from all over the farm to fork continuum, including harvesting, packaging, transporting, even occur in your own home. And so contaminated irrigation waters have been shown to effectively transmit pathogens to crops and their soils. And several large investigations into multi-state foodborne outbreaks have identified contaminated irrigation water as the most likely cause of the outbreak. And this included water from small irrigation ponds. And so major pathogens of concern, this paper I think came out yesterday, so I quickly took the image from them. Salmonella and different types of pathogenic E. coli are responsible for the most amount of foodborne outbreaks in the United States, and then followed by Listeria and Campylobacter. And it is difficult to enumerate pathogens in the environment due to their transient nature, as well as things like confirmation testing. It takes a long time, and it's tedious and requires elevated biosafety. So the US EPA mandated that microbial quality of water would be determined by measuring generic levels of generic E. coli in water sources, and they did this for recreational waters. And so in this sense, generic E. coli serves as a fecal indicator bacteria, since levels of them, E. coli have been positively correlated with the presence of pathogens, as well as number of illnesses per 10,000 individuals. And currently, for microbial quality of irrigation waters, the FDA mandates or regulates this under the Food Safety Modernization Act, or FSMA. And under FSMA, there's the Produce Safety Rule, or the PSR, and this actually adopts the limits of generic E. coli allowed in the water source right from the limits made for recreational waters by the EPA. And then specifically, those limits are a concentration of less than 2.1 log CFU, or colony forming unit, in an irrigation source, with a 90th percentile value having less than 2.61. And farmers are required, or farmers or water quality managers are required to test their waters periodically, usually in the growing season. But if these numeric criteria are not met, then they must perform corrective measures. And some of those may include delaying the time between irrigation and harvest, as well as treating the water with antimicrobials or other chemical substances. But a recent survey found that most farmers and water quality managers would rather be proactive with their irrigation water quality rather than take corrective measures later on. And so some of the problems here is that the PSR, the Produce Safety Rule, does not specify where or when to take a sample, other than as close as practicable to harvest. And it's been extensively shown the levels of fecal indicator bacteria in the environment are highly variable in both space and time. And this variability is not accounted for in microbial water quality studies or the mandated testing that's supposed to reduce the incidence of foodborne outbreaks. Often only one sample is taken from an undisclosed location within a water body, and rarely is the time of day reported in the literature. So with that, the overall problem statements are that if these FIB populations demonstrate large spatiotemporal variability, then the choice of where or when to sample should not be made arbitrarily. And currently, with approved methods, microbial water quality determinations take roughly 18 to 24 hours to complete. And this means that they're not really representative of current conditions. And so predictive models may be able to improve the timeliness and accuracy of microbial water quality assessments. With that, the condensed overall objectives of the study were to elucidate the spatiotemporal variability, primarily by looking at 2- and 3-dimensional variability within single dates and across seasons. Also looking at diurnal variability in E. coli concentrations. And then we want to use, compare several machine learning algorithms for their ability to predict E. coli concentrations based on levels of continuously measured or rapidly measured water quality variables. And so with that, the first study specific objectives are to determine if there are locations within irrigation ponds that are consistently higher or lower than the average E. coli concentration, identify sampling locations that are representative of the average across the pond, and investigate if the above patterns can be expected to be persistent across multiple years of observations. Finally, do these spatial patterns of E. coli concentrations correlate with patterns of other water quality variables? So not point-by-point correlation, but correlation in the patterns of them. And so the 4 study sites that are used in this first study so pond 1 is in Central Maryland. It has 23 sampling locations. I have the outflow where the irrigation is withdrawn from, as well as inflows and ephemeral inflows marked on the bottom left of the graphic. Pond 2 is on the eastern shore, and has 34 sample locations. Pond 3 is down the road on Soil Conservation Road. You'll notice that it's one of the only ponds that has a solid green area because it has constant influx of groundwater at a rate of roughly 3 liters per minute or so. And this groundwater is high in conductivity as well as E. coli, which will play into a factor later on. And Pond 4 is on the same property as Pond 1 and has 16 sampling locations. It is creek fed at the bottom left. And so when the water level drops, it starts bringing in water from the creek. And so in each chapter, I'm going to go over specific methodology, but this is just general, which applies to all the studies. So ponds are sampled roughly every 2 weeks during the growing season. Pond 1 was sampled from 2016 to 2020, Pond 2 from 2016 to 2021, Pond 3 from 2020 to 2021, and Pond 4 was only sampled in 2016. Sampling was not conducted close to rainfall or runoff events because we wanted to characterize conditions that were emblematic when irrigation would take place. People don't irrigate after it rains. Sampling was conducted in grid-like fashion, as we just saw from the sampling maps. It was always carried out in the morning for about 9 to 10 or 10:30 a.m. And samples were collected and immediately placed on ice in the dark cooler, and processing usually took place within several hours of collection. Then general methodology continued. We used EPA method 1603, which is membrane filtration and modified MTEC method to enumerate E. coli concentrations. In every single location that a E. coli sample was taken, a YSI XO2 sonde was used to characterize dissolved oxygen, temperature, specific conductivity, turbidity, fluorescent dissolved organic matter, chlorophyll A, and phycocyanin. Additionally, we used a COAQ 300 discrete nutrient analyzer to measure concentrations of orthophosphate, nitrate, nitrite, and ammonia. A variable TOC nutrient analyzer to measure different forms of dissolved carbon and total nitrogen. We took depth and secudis readings where we could, or depth permitted. Surface and submerged photosynthetic active radiation measurements were also taken in the ponds, and weather data was acquired usually from on-site stations, but sometimes just the closest station nearby. And for this first study, the main pattern analysis that we're using is this mean relative difference, and this was proposed by Picard in 1985 for finding locations across an agricultural field with soil moisture contents that were representative of the rest of the field, or approximated the average closest. And so how this is done is you go to the pond on one day or your field or wherever, and you determine a relative difference for each sampling location by taking the measured concentration, subtracting the average, and dividing by the average. So the relative difference is relative to the average value or the spatial average across the pond. We then do that multiple times within a sampling season, so say 6 to 10 times. And then at the end of the season, we have each of the locations has maybe 6 to 10 relative difference values. We then take the mean or the average of this value, and this is our mean relative difference. And on the next slide, I'll kind of take a second to explain how to interpret this. So with the mean relative difference, the locations that are in blue, and how they are separated right now is I took the interquartile range, so everything in yellow is 25 to 75% of the distribution. And locations that are blue are consistently below the average, and locations in red are consistently above the average. And the locations in yellow best approximate the spatial average. And the best approximation comes from those closest to 0. So in this case, it'd be locations 15 and 4. So what we see from this pond through the multiple samplings of 2016 is we saw consistently higher concentrations near the inflow where the creek will let water in. There is a good degree of error on the sampling locations, probably related to whether or not this creek was contributing water to the pond during sampling or not. We also see kind of a diffusion of concentrations further away, with some exceptions like location 5, which was a very stagnant shaded area. And then kind of a theme that we see with some of our ponds is that the interior locations typically have lower concentrations than those on the bank, which we'll continue to see. But on average, location 1, which is at our highest point, the highest mean relative difference, was on average 101 times greater than those locations in the center, the yellow. and 150 times greater than those in blue. And one of the takeaways here is if locations 1, 2, or 16 were continuously sampled, this pond would have been out of compliance according to the Produce Safety Code. Continuing on, this is the soil conservation road pond. And we see that the error bars are quite large, but when I put this on the scale as the previous pond, we get a very flat line of the MRT curve. And this gives some kind of indication that a sample could be taken at anywhere in the pond and be representative of more or less the average. However, with that said, if we look at the difference between location 12 and location 10, there was on average 74% difference in the concentrations. And now this is, I should have mentioned, we're going backwards, pond 4, 3, 2, 1, just in terms of the amount of data. So this is pond 2, which is on the eastern shore. And I have a line down the middle with 0. And what we see is locations 25 to 34, which are pretty much down the center of the pond, are consistently below. And this is only 2016 data. Whereas those on the bank are usually higher, but more about the spatial average. Overlaying the next year of observation, so coming back in 2017, we see that the patterns are largely preserved between sampling years, with some exceptions noted on the slide, but still a pretty good pattern match for completely different years of observations. Finally, the 2018 data laid on top, we do see that the 2018 data is more similar to 2016 than 2017. But again, we see this consistently lower bunch of the interior locations across the pond, whereas the baked ones tended to be consistently higher. Now, if we make a 3-year mean relative difference curve of this, we can determine locations that are consistently higher, consistently lower, and consistently about the spatial average across the pond. And the usefulness in making charts like this is that one, we can identify hotspots, so locations 22, 21, 12, 23, and try to hypothesize on why these locations are consistently higher, and vice versa, why these locations are consistently lower. And some of the things that we found at this pond is, I mentioned 21, 22, 23. There's a property here with a septic system, as well as domesticated dogs that roam free in the yard, which could have some bearing on the elevated concentrations of fecal bacteria. As well, it's a very shallow area where there could be more mixing of sediments with the water. We also see that location 12, it's a little bit hard to tell, at the top, as well as 34 here, are from the ephemeral inflow. So there's a forested area at the top of this pond, which has deer in it, and the higher concentration of this area could be related to this entryway of E. coli into the pond. And then just like what I was saying is that these blue locations are consistently those found in the interior of the pond. The second useful part of this map, or chart, is identifying locations that approximate the spatial average. So if I, with all the observations I've made over the years, I could identify some of these locations that more or less represent the spatial average and get a better idea than if I were to just go down to location 1 and take a sample. It might be much higher than the spatial average or much lower. So those locations in yellow better approximate that spatial average. There's also consistency in the patterns between years, as I was pointing out, but if we want to look at that statistically, we look at Spearman correlations, which is basically how close the rankings continue between sets of years. And we see that in every year, every pair of years, there's a significant positive relationship between the ranks of the locations in terms of from low to high. Going to pond 1, a similar pattern. Locations 1 through about 10 are locations that are on the banks of the pond, whereas 11 through 20 or 19 on this slide are all those on the interior of the bank, pond. Overlaying the 2017 data on top of 2016, again, we see that this pattern is largely preserved in completely different years of sampling, with some exceptions. Notably, locations 16, 18, and 19 in 2017 became further away from the spatial average. And then locations 20 through 23 were only added in 2017. Adding the 2018 data on top of that, We see again that the 2016 and 2018 data are more similar than that of the 2017, but again, the pattern is largely preserved across separate years of sampling. And then finally, the 3-year MRV curve for this pond, we see that location 21 is consistently higher with a good deal of error. And this is the location closest to this ephemeral inflow, which drains a forested area with animals in it. And the error on this could be associated whether this inflow was occurring or not, the rate at which the flow was occurring. Additionally, locations 8, 1, and 9 are all on this bank. And this is where waterfowl tend to enter the pond, as well as the owners of the pond enter for recreational purposes. And then similarly, locations at the far end are made up of the interior locations of the pond. And again, we can identify locations that are very close to 0 on here, which best approximate the spatial average across the entire pond, which gives you the best idea of what the E. coli concentration is. And then looking at just like we did with the previous pond, the consistency and the patterns between years, we see that there's a significant relationship in the order and the ranks of the locations for every set of years. But again, the 2016 and 2018 has a Spearman correlation of 0.842, so a very close ranking of patterns for completely separate years of observations. And like I mentioned, we can make these MRV curves with concentrations of E. coli, but we can also do it with any one of our water quality variables. And in this sense, we're not making point-to-point correlations anymore. It is patterns of E. coli with patterns of pH, patterns of temperature. And what I just want to point out, because there's a lot of numbers on here, older significant relationships, are that the direction of the relationships for both of these ponds with multiple years of observations are identical. The same sign of the relationship. Now, the significance and the strength differ, though. And this could just be related to site-specific characteristics of these two ponds. So, conclusions of the first study that we observed stable spatial patterns of E. coli in the study ponds. These patterns were similar across multiple years of observation when we had that data. The mean relative difference between some locations was substantial, which may alter the outcome of a microbial water quality survey. If you continue to sample an area of low concentrations or high concentrations, you may be over or underestimating the real risk. Increasing the sampling density revealed information otherwise not realized, including hot and cold spots within the ponds, which could later be identified or related to sources or pathways of E. coli from on-land practices or inflows or things of this nature. And banks generally had a higher concentration than the interior of the pond. And why we think this is happening is because the interior of the pond is open and gets a lot of sunlight, solar radiation, which has been known to deactivate E. coli concentrations in water. And the banks generally had, they were more shaded, there was vegetation on the banks. As well, these are the banks are the area where anything enters the pond, whether it be water running off or animals coming in. So that's what we're thinking is the rationale there. And taking a single sample from an arbitrary location is likely not representative of the pond-wide average, but there are locations that can be identified that better represent that average. In the sake of time, I'm just going to march along. Content in chapter 1 not shown today. We also use geographically weighted principal components or empirical orthogonal functions, if you're familiar with that. And this can decompose the spatial and temporal trends or variability. Additionally, we use the EFPC model along with 3D data sets to simulate the withdrawal of irrigation from pond 2. And what we did was determine how the 2D and 3D variability of E. coli concentrations in the pond resulted in temporal variability at the field. And so if that sounds interesting, I recommend you read the dissertation. Going right to the third study, which is diurnal variation of E. coli concentration. The problem statements here are that most microbial water quality studies do not report the time of day which samples are taken, nor does the produce safety rule indicate when to take a sample. In a couple of studies, I did a literature review recently, and maybe 2 of 40 studies reported that samples were taken before noon or before 11, citing the effects of solar radiation. This is important because of the viable but non-culturable state that fecal bacteria and pathogens can enter. And this is in response to environmental stressors such as sunlight, changes in dissolved oxygen or pH, where we can bring these samples back to the lab, and these bacteria will not grow in our agar plates because they're in a kind of a dormant state, a survival mode. But overnight they can recover, and they're fine by the morning, and this cycle continues. If significant diurnal variability is present, then this may also alter the results of microbial quality assessments. With that, specific objectives were to determine within-day variability by taking measurements at multiple time points, and identify the leading water quality parameters which influence the concentration of E. coli throughout the day. For this study, we focused on ponds 1, 2, and 3. For ponds 1 and 2, the sampling maps are different, less locations, because we are increasing the temporal component of the sample. And so specific methods for this study are that samples were taken at 9 a.m., noon, and 3 p.m. Over the course of 2019 and 2021 at different intervals we'll see for the different ponds. We used a one-way analysis of variance to determine if time of day was a significant factor, and used pairwise testing to compare individual time points. We calculated E. coli die-off rates or inactivation rates within the ponds, and we used conditional inference trees to determine the leading environmental covariates. And if you're familiar with regression trees, they're very similar, but the splits will not occur unless the groups and the terminal nodes are significantly different. If that doesn't make sense, when we get to that slide, I'll try to better explain that. And I hate to always throw a huge wall of numbers up, but I've tried to highlight what I thought was important. And so these are all the raw numbers for the water quality variables in the ponds, pond 1, 2, 3, left, center, and right, respectively. I've highlighted the concentrations of dissolved oxygen and pH in the ponds, and I want to note that in all ponds, throughout the day, both of these increase due to photosynthetic activity. But in pond 2, the magnitude of the increase is much greater than the other ponds. If we then look at what's highlighted in green, which is phycocyanin and chlorophyll A, which are photosynthetic pigments that we measure, or sorting measurements for cyanobacteria and algae, we also see that pond 2 has a much higher concentration of these, or several times higher than the other two ponds, which I think may play importance in coming slides. So again, this is the raw data for all of our observations. The ponds are colored differently and labeled on the left. On the x-axis, we have the time of day. On the y-axis, we have the logarithmic E. coli concentration. And what we can see more times than not, especially in pond 1 and 2, is this trend of highest concentration in the morning hours and a gradual decrease throughout the day. It's not perfect. There are definitely observation dates that violate this observation, especially with pond 3, where 3 of the 4 dates there was literally a decrease through the day, but it was very minimal compared to the other ponds. And just to escape this large amount of data, here's a summary of what we just saw. So ANOVA significance time of day is a factor. Pond 1, 3 of 5 dates, it was found significant. Pond 2, 6 of 8 dates. And pond 3, 0 of 4 dates. The time of the highest concentration, average concentration in all ponds was 9 a.m. Important to note the asterisk here in all but one observation. The time sequence of the average concentration decreased from 9 a.m. to noon to 3 p.m. And then we could look at the average reduction in E. coli concentrations throughout the day. And we actually see that for pond 2, there's incredible decrease, especially looking from 9 a.m. to 3 p.m., an average decrease of 568% concentration. Related to the average reduction, you calculate the inactivation or die-off rates in E. coli. And we see that pond 2 contained the highest die-off rates, with pond 1 serving us about half of those, and pond 3 serving about half of pond 1. Moving forward, looking at the environmental covariates responsible for creating the most homogeneous splits in the data set. For pond 1, is a very simple split, levels of dissolved oxygen. And so the threshold value for the DO concentration as affecting E. coli concentrations was a value of 10.4. If the dissolved oxygen was greater than 10.4, we had effectively 0 mean E. coli concentration in the pond. If the concentration of dissolved oxygen was less than 10.4, we had much higher concentrations of E. coli in the pond. Now for pond 2, pH was the leading splitter of the data set with a threshold value of 8. Below 8, turbidity or NTU was the next leading splitter. And on the y-axis, I should point out this is log E. coli concentration. With higher turbidity, we get higher E. coli concentrations. This agrees with the literature in terms of solar shielding and the preference of attachment to particles than planktonic existence for E. coli. And if the pH was greater than 8, then orthophosphate concentrations determine the next leading split of the data set. And the higher the orthophosphate concentration, the higher the E. coli concentration. This may make sense because there's more nutrients to provide for growth and persistence in the pond. And perhaps the growth that was demonstrated kind of subverted some of the diurnal effects of the solar radiation or temperature changes, dissolved oxygen throughout the day. For pond 3, the levels of specific conductivity were the leading splitter. And this is probably due because of this constant inflow of groundwater, which had very high conductivity levels. But below a level of 90.7, turbidity again was the next most important splitter. Same directional relationship as for pond 2, higher turbidity, higher E. coli concentrations. To the right, we get dissolved oxygen, and to the left of that, with a less than 9.07, we get temperature as the next most leading environmental covariate for the E. coli concentrations. With higher temperatures came lower E. coli concentrations. This is also something we'll see in the literature. Now, conclusions of this study with the diurnal variability in E. coli concentrations was well pronounced in ponds 1 and 2, and typically went in the order of 9 a.m. to noon to 3 p.m. Pond 3 did not show strong diurnal trends, although concentrations did decrease in 3 of the 4 observation days. And may be related to this constant groundwater inflow with high conductivity and concentrations of E. coli that were typically 4 or 5 times the average across the pond. Die-off rates between the ponds were different, as were the leading environmental covariates, but both pH and DO were selected as leading splitters of the data set. And we know from the literature that changes in pH and DO, particularly in the presence of sunlight, have been shown to induce fecal bacteria die-off. And this goes in the way of photosensitizers creating radical oxygens, oxygen radicals, including hydrogen peroxide or superoxides, which are harmful to bacterial DNA. P3 had specific conductivity as the leading covariate, and again, maybe related to this constant groundwater inflow. P3 also had very low changes in pH and dissolved oxygen throughout the day, and very low concentrations of photosynthetic organisms, which may explain why the fluctuation wasn't very great. Chugging along, the 4th study in the dissertation is entitled Prediction of E. coli Concentrations in Agricultural Pond Waters, Application and Comparison of Machine Learning Algorithms. So as I mentioned, microbial water quality determinations according to approved methods are tedious, and they're not representative of current conditions if it takes 18 to 24 hours to enumerate the bacteria. These data sets are also highly complex and contain nonlinear relationships between the inputs, or water quality variables, and the output, which is our E. coli concentration that we're trying to predict. So the objectives of this study were to evaluate several machine learning algorithms for the prediction of E. coli using readily sensed or continuously sensed data, test several sets of water quality variables from simple to intermediate to complex to see if an increased number of predictors improves the performance, and determine the most influential predictors of these E. coli concentrations. So I wanted to spend a lot more time on machine learning and the specific algorithms that I used in this study, and the more I tried to do that, I just realized that there was not enough time to do it. It could be kind of its own seminar, so this is just going to be a very brief coverage of this. So machine learning is a branch of artificial intelligence. It's probably one of the most important ones, as it powers the rest of these branches in terms of teaching or creating algorithms that learn on their own based on training data that's fed to them. Machine learning can further be broken down into unsupervised learning, reinforcement learning, and supervised learning. And today we're going to focus on supervised, specifically regression tests or predictions. And so then what is machine learning still? I'm not going to read all the definitions in the center slide, but these are some common ones that come up through Google. And so it's used in many disciplines, including financial services, healthcare, transportation, retail, as well as natural sciences. And I'm sure a lot of you have encountered machine learning applications in respective disciplines. And the popularity of these waxes and wanes and somewhat dependent on the computing power. But in microbial water quality studies and water quality management, machine learning is becoming very attractive again. However, there's little in the way of hypothesis testing with machine learning at this point. It's mainly exploratory data analysis, but this is all changing, and I expect there to be changes in this in the next couple coming soon. So specific methods for the sports study is that we use the carrot package, which is a package in the R programming language. And I tried to come up with a small conceptual sentence for some of these algorithms to try to get closer to what they're doing. But we used gradient boosting machines, which effectively take many small steps in the right direction. K-nearest neighbors, which looks at familiarity in the training data set to label the testing data. Random forest, which is effectively hundreds or thousands of individual regression trees, which at the end all vote for a prediction. And this could be thought of as wisdom in numbers. Support vector machines, which are could be thought of guardrails to guide our decisions. They split data sets using these support vectors and penalize incorrectly classified data. And then I have multiple linear regression just as a very interpretable baseline model as to what to compare the other machine learning models to. Now, with machine learning algorithms, you need to train and test them. So you'll have your data set. And what's traditionally done is there's about a 70-30 split of training and testing data. So 70% of your data will go to training the model. And then when you go to test the model, you use the 30 remaining percent. And this is data that the model has never seen before. And it is asked to make a prediction based on the training data. And so for this specific endeavor, we actually use 10-fold cross-validation, which subdivides your data sets into 10 equal parts. 9 of those parts are used for training, 1 part is used for testing. The fold meaning in this means it's done 10 times with random subsets of the data. And then at the end, the prediction or the metric, whether it be root mean squared error or R squared, are then averaged. So in this data set, we used Pond 1 and Pond 2 3-year data sets, which are our largest ones, included 900 samples, and with the water quality variables, about 8,000 unique measurements. There's minimal pre-processing. We did remove rows with missing data, but we did not, no imputation was used. And control parameter tuning was done during cross-validation. Now, I mentioned these predictor sets from simple, intermediate, and complex. I have them listed here, but each set builds on the next one in terms of the number of measurements and the complexity as well as the cost of performing the measurements. I mentioned the 2016 to 2018 data were used, and for some years, the ABC set could not be used in 2016 because we did not have nutrient data at that time. So some sets are only applied to certain years. For our mean metric, and what we'll look at today is the root mean squared error, which is the standard deviation of the residuals. We also calculate R squared and mean absolute error, and I have that in the back of the slide if that's of interest. And unfortunately, the results of this stuff are just boring to look at, but I would go ahead and kind of highlight what I'm going to talk about. So Pond 1 is at the top, Pond 2 is at the bottom. You have the algorithms, there are variations on the far left. And we see that gradient boosting machines provide the best, lowest error for the 2016 data set with predictor set A, so the simple predictor set. Support vector machines is the best in Pond 2. But that's kind of where this ends. And in pretty much all other predictor sets and across years of observations, the random forest model performed the best and provided the lowest error. I also want to point out that in a lot of cases, the root mean squared error across the machine learning algorithms are pretty similar. They're not substantially different in a lot of cases. And also that the multiple linear regression consistently provided the worst predictions compared to the machine learning algorithms. Now, I mentioned that the metrics were pretty close between random forest and some of the other models. This is statistical comparison using a special t-test for cross-validation. And this is comparing specifically our best model from the previous slide, the random forest, with each other algorithm. And pond 1 is on the left, pond 2 is on the right. And what we see is that the performance in the gradient boosted machines in the random forest was very similar, very high p-values in terms of the similarity. For the other algorithms, there's a little bit more of a spread. For pond 2, there's much more of a spread in terms of their performance. In fact, there are 2 instances where the random forest performs significantly better in its predictions than the k-nearest neighbor algorithm. Then through this endeavor, we can use recursive feature elimination and basically identify the most influential predictors of the E. coli concentration. And so pond 1 at the top, pond 2 at the bottom, different variable sets from left to right. And there are some similarities between the 2 ponds in terms of the most important predictors being specific conductivity and temperature for the A and AB sets. They may be flipped, but they are top 2 in both of these instances. Now, in the AB set, the first instance where fluorescent dissolved organic matter is introduced, it becomes important out of the top 8. And then actually in the ABC data set, it becomes the most important predictor of the E. coli concentrations, along with specific conductivity, chlorophyll, and then the first year that we introduce total nitrogen and total carbon, these become up there with the top most important variables. And it's important to note that there are no directions of the relationships here, and that's mostly because they are nonlinear relationships. There are clusters of your data which positively correlate with temperature, negatively correlate with temperature, and this exists for all of the predictors in their response on the E. coli concentration. Now, this is specifically looking at the expansion of the predictor set. So on the x-axis, I have predictor set A, AB, and ABC, and I have, again, what those are at the bottom here. And then pond 1 and root mean square error is on the y-axis. In pond 1, we see that there's hardly any benefit from increasing the predictor sets between A, AB, or AB, ABC. However, pond 2, there's almost no improvement when we go from 5 to 8 predictors. But there is a decrease in the error when we go to 12 predictors, incorporating this nutrient data. However, in the grand scheme of things, this is not really a big decrease in error. So conclusions of this study are the random forests by and large perform the best across the data sets, but the best model is often data set dependent. And it should not be assumed that the same model is going to do the best in every data set. And this is somewhat evidenced in the work where support vector machines or gradient boosted machines did better than the random forest. Model performance was rarely significantly different, but there was consistency in the random forest becoming the optimal model in most cases. The 2018 A, AB, ABC data set showed that a simpler suite of water quality variables could be used to accurately predict E. coli concentrations, and that some of these larger predictor sets may not be necessary. And that the importance here is that with each additional predictor that you include, that's the cost to buy that sensor, that's the training for someone to use it, and maybe lab analysis and time and effort to use the sensor. And so models created using machine learning algorithms show promise for conducting quick or real-time microbial water quality assessments, especially if continuously or in situ data can be used. And they tend to do much better with these complex data sets that are, have a lot of nonlinear relationships within them. And then, so just overall conclusions and recommendations of this work, I recommend to perform pilot studies to determine spatial variability initially within a water body, and this could be used to identify sources or pathways of E. coli or just hot and cold spots within a pond. If dense sampling cannot be done, then a composite sample from multiple locations is the next best bet. If one elects to not sample the pond itself, but the water that reaches the field, then samples should be taken at different time intervals. Because what the simulation study we didn't cover today showed is this 2D and 3D variability within the pond water translates to temporal variability at the outtake of the irrigation water, as well as diurnal variability will change concentrations throughout the day. So a single sample will not be representative. Sampling at or before 9 a.m. gives the most conservative estimate of risk, especially if this viable but non-culturable state is possible with fecal bacteria and pathogens. And then again, machine learning algorithms show promise for conducting quick microbial water quality assessments using readily sensed measurements. I would like to then just acknowledge the members of the Microbial Food Safety Lab, the farm and research directors, especially private landowners that allowed us to work on their property, and then also the interns that we could not have done the work without. And with that, I'll take any questions.
Questions for that?
Yes.
So on your data, specifically when you're looking at diurnal, did you take into account like any weather station data in terms of like solar radiance on that day? Like if there was cloudy day, sunny day, et cetera?
So one of the inputs in this data set is the photosynthetic radiation. And surprisingly, it wasn't chosen as a leading predictor. Because usually what you're reading is that, with solar intensity, the die-off is increased. So that was surprising.
So it was included like from a weather station, like the hours of radiation, or what was it?
In situ sensing. So we had meters that we took into the water. So we would measure it at the water surface and then submerged at 3 different depths and took the average of that.
Right.
Now,
so while you were taking the sample, it was the solar radiation at that time.
yes, at that exact location.
Right.
There is more work to be done in terms of incorporating weather station data, in terms of days since last precipitation, average solar radiation, 1 to 2 days before, 2 to 5, this kind of stuff.
Yeah.
So I do want to continue down that route because weather station data is probably the best thing you can get.
Yeah.
So.
And then what about going back to some of your things with, there was one where you had like nitrogen data plus, you didn't have the nitrogen data, keep going. You didn't have the nitrogen data highlighted, you had other data highlighted. Keep going.
Is it?
Not Statistical.
Oh, yeah, no. Okay.
There you go. Yeah. So I'm wondering if so you talked about again the effects of DO, and that makes sense, and the effects of pH, and those are what came out. But again, I would think your chloroform would be directly related to your nitrogen and phosphorus, which you talked about a little bit. But I'm wondering if, again, if we're looking at coliform and the specific effect of that on E. coli, I would think if you have a lot of like infrastructure in there, you have more microbial biomass because you have more like stuff in the water, right, in terms of coliform. And so if you're seeing more dissolved oxygen produced during the day, I would think too, you would just have more microbes that are in there. So then more of them would have an E. coli or something. Do you see what I'm saying?
Yes, yes.
That connection.
Yeah, and I did forget to mention these are highly oligotrophic ponds. The nutrient levels are very low. Oftentimes they were hard to detect. And so really you can see kind of locations. They teetered at detection limit kind of.
Right, so the highest you were getting was like 0.18. So
Yeah,
0.18 milligrams per liter is the highest ammonia rate that you actually got.
Yeah, so our nutrient analyst would just come to me and say, I wouldn't use these values because they're too low. Or,
Okay.
but looking at this pond too, which you just made mention to, this is actually it. And if you look at that water,
Yeah.
the other ponds we can pretty much see to the bottom of. This pond stands out entirely. And that's what I was trying to point out, the different levels of the phycocyanin and the chlorophyll A surrogate measurements. So this is a different beast entirely. I do believe it's why we see such high spikes. And some of the DO goes up to 20 milligrams per liter at some points of the day. And just, what we see from retention ponds and disinfecting is that high DO usually is lethal to coliforms and whatnot.
And then the ponds that you did, you started out, I remember the first thing when you were going back through the data, you started with pond 4, right? And then you were back to city pond. You don't need to go all the way back there. But I think pond 4 was the only one where you actually, it was above the limits, right? None of the others were above the limits, or is that not right?
No, so the last minute I took out actual concentration data.
Okay.
So in this, it's all, none of the actual concentrations are seen. That is, I had all these slides where I wanted to go over machine learning.
So which ones were actually above the limit, and how does pond 2, did it have more above the limit with all that foliform or less above the limit compared to pond 1, 2, 3, 4?
Okay, so pond 2, we see the concentrations in logarithmic scale on the x-axis. So let's do -1 to 3, so 3.5. The concentrations really weren't substantially different between ponds 1 and 2. There's something more I wanted to say. Oh, okay.
So which ones were above the legal limit?
Actually, none of them are. They're all very clean ponds.
Okay.
The thing is, we take so many samples that we drive down the effect at the high locations. Nobody takes this amount of samples. This is purely research. But what I try to point out with pond 4 is if you were somebody and you're just trying to get the simplest sample you could, you kind of like walk into the pond in this part. So locations 1, 16, and 2, if those were consistently sampled, you would be hurting yourself by reporting artificially high. The concentrations are high there, but if you take the average across the pond, they're much lower.
But even so, they were never above legal limits.
In these locations, there were, but it's this whole geometric mean, right? I kind of didn't put that part into the farmers are required to take 20 samples over a 2 to 4 year period and come up with a profile, and then they'd have to take 5 samples a year after that, and then they have a rolling data set, and that 2.1 log is the geometric mean. If they were to continue sampling from these locations, they would have been above it. But not because we sampled so much, we drove the averages down. But yeah, I didn't want to incorporate concentration data. I just was worried about time.
Yeah. Okay, very interesting.
Yes.
Hi, I have a quick question. I was wondering if you knew how many of these ponds exist out there. Like, are they very common or not really? And then the second part of my question is, are the design, the origin of these ponds, are they part of like a present or past like conservation initiative for farmers?
So the first question, sorry, what was it again?
How prevalent are these?
Extremely. There's a paper, I think it's 2014, that said there's like 9 million ponds on the East Coast or something like that. So there's a lot, and some of the future work that I also have to cut out is that we've started sampling ponds in Georgia as well as looking at depth sampling there and study of pathogenic bacteria. All of the ponds that we work with were specifically designed for irrigation purposes. So they're a little bit deeper than a stormwater or retention pond. They're not designed to hold nutrients or runoff. They are designed to provide clean water to crops. As far as conservation efforts or anything, I'm not sure. Yeah.
I had a question. I'm not a hydrology person, so I just had a question about how you did the actual sampling. Like, I know, like, there's all the oxygen and stuff, but was there, like, is this surface level water? Are you, like, dredging the bottom, or you might have touched on the beginning and I missed it?
No, probably skipped it. Everything else. This is a platform that we use sometimes. We typically be in a small hanging boat, and the majority of what I showed today is all surface samples because that is 99% chance what somebody is going to go collect.
Sure.
The farmer's not going to go in and take a sample 3 meters down. That's much more difficult to do. So the majority of what I showed today is all, we would say, in the top half meter of the pond water.
Cool.
And so specific chapters of this work actually go into 3-dimensional distributions, we call that, and water quality variables. So we can determine the gradients in these ponds. And just a little spoiler, there's higher E. coli concentrations with depth. And that makes it a little bit more tricky when you're trying to take a sample at the surface, which probably really isn't representative of what's below.
Right.
And when we're initiating irrigation, the water is not coming directly from the surface, it's coming from all parts of the pond. So there's a lot of implications there in terms of, how monitoring should be going and should depth sampling be done. But I do want to just finally mention that pond 3 was about 3.5 feet deep, and that was one that there weren't substantial differences between surface and bottom because the gradients probably weren't allowed to form.
Sure.
Due to temperature dissolved oxygen. So if any of that sounds interesting, like I keep repeating myself, please reach out to me or read the dissertation once it's out one day.
Thank you.
Yes.
You briefly mentioned bathymetry. Was that useful?
So that is this, I tried to make a graphical abstract for this really quick last night. But pond 2, we took very in-depth bathymetry data. So pretty much every 1 meter, we took a sonar sample. And as well, we did depth sampling here. And so this was pivotal for operating the environmental fluid dynamic code, this EPA simulation, hydrological simulation. And so all that data goes into that code for where the water is coming from, what the depth is, the velocity that it's coming at. So that what the bathymetry data there was pivotal. In all the other locations of the other ponds, we only took a depth sample, like where the sample location was. So we don't have as much in detail bathymetry as this pond. But that's kind of like future work. We hope to continue down this road and try different variations of the simulations. Yes.
So did you really publish 3 or 4 so far? They're all impressed and published new chapters.
For the most part, we have one in Frontiers of Artificial Intelligence now. It had 2 positive reviews. I need to respond by the 14th. And that was the later part of what I was showing.
So you're gonna basically have a slam dunk dissertation.
That's what we're.
Congratulations.
The date's not set.
Okay.
Wait, when you get that?
Publications.
What's we have a plan?
A plan.
For what you're doing there.
I'm hired to the USDA. I've been a contractor for 8 years. I'm hired to next July. I hope in the new year to decide where to go. Right now, it's like daunting to think about it with everything else going on, like today's presentation of the dissertation.
Yeah.
So my boss at the USDA has supported me kind of that time to look around.
Yeah.
So,
Very nice.
thank you.
Well, congratulations, John. Well done.
Thank you. Yeah, excellent. I think we should wrap up. People might stay back to them to make their forms on the table back there.